Okay, so big idea 4 is all about rates of chemical reactions. So the very first thing we have to be able to do, if we're going to talk about big idea 4, is to know what the heck a rate is. So for chemical reactions, what we're interested in terms of a rate, how fast something is happening, the rate in a chemical reaction is how fast the things are being consumed or how fast things are being produced. Okay? So for a very generic type of reaction, (2A plus B yields 3C), we might see, if we are able to monitor these substances, we might be able to keep track of what their concentrations are versus time. Okay, remember this symbol right here in the brackets? That's concentration. All right, we might find that for substance A, its concentration decreases linearly over time. Okay, so we have some reaction. A is just being consumed, so it starts out at some high concentration, and its concentration decreases. Right? Well, on this graph of concentration versus time, we can calculate the rate of the reaction by finding the slope of this line. Right? A rate is a change in something over change in time. Since we've got concentration as our something, we've got time here. If we look at the change in concentration over the change in time, that'll give us the rate of the reaction. Okay, but for this red line that I've drawn, what we're really calculating here is the rate in terms of the change in the concentration of substance A over time. If we started with an equal concentration of substance B, how would the graph of its concentration versus time look?
Would be half as steep
Half as steep. Why?
because that's like there's twice as much, so it's going to happen at a faster rate.
There's twice as much A consumed per reaction as there is B per reaction, so B's concentration should be changing half as quickly, right? If we started at 10 molar here for the A, and we got down to 5 molar here in a given amount of time, let's say this is 10 seconds, well, if A changes by 5 moles per liter in 10 seconds, B should change by 2.5 molar in the same 10 seconds, right? So the slope is going to be less for B than it is for A. Okay, but we could still define a rate here in terms of the concentration, change in the concentration of B over change in T. But those rates aren't going to be the same, right? So there is an issue when you are talking about the rate of a reaction. You have to define what it is you're basing that rate on. Am I basing it on the change in the concentration of a reactant A? Am I basing it on the change of a concentration of reactant B? Or I could even base my rate law or my rate on the change in concentration of C. How is that going to look? How is the graph for C going to compare to A and B?
3 times as much as or B is a third of the
So the speed at which B is changing is 1/3 the speed at which C is changing, right? Or we could say C is changing 3 times faster than B would be. However, the other big difference is that C is being produced, right? So instead of the graph going down, for C, if I color it orange, it's going to go up. And it's going to go up quickly, right? So in the same 10 seconds, if B is going down, what do we say, 2.5 molar in 10 seconds. If this goes down by 2.5, this should go up by 7.5.
7.5.
6.
We're so good at math.
Okay, so that thing's gonna go up, right? Now eventually, these things are gonna hit the point where we run out of one of them. Looks like A is gonna run out first, and once A runs out, concentrations are gonna remain constant for the other ones, right? So it's a sort of limiting reactant situation here. Okay, so again, I could define the rate in terms of C. Say the rate is the change in the concentration of C over change in time. Okay, so again, if you're given information about a rate of a reaction, they're going to tell you this rate is giving us how much B is being consumed or how much C is being produced. Usually, we want our rates to be positive, so usually we pick one of the products and define the rate in terms of the change in product concentration over change in time.
Could you find the rate of C by adding the rate of A and B together?
Adding them together, I have to think about that. In this case, I suppose, yeah. Is that always the case? I'm not sure.
Okay.
I'd have to think about that. That's a good question. What we normally do, though, is we define rates in terms of each other. Okay? So, if we did what I just said, if we define it in terms of the change in concentration of C over time, well, because of the stoichiometry of the reaction, that is going to be proportional to the other rates. Okay, but we might want to think about how. If we're defining this as how fast C is changing over time, and that's the rate of our reaction, how does that compare in terms of the change of the other ones over time? So how does the rate of change of C over time compare to the rate of change of A over time? Well, what did we say? This was 2.5 molar in 10 seconds, so 0.25 molar per second. This one was 5 molar in 10 seconds, so 0.5 molar per second. And this one we said was 0.75 molar per second. Actually, these are both negative, right? The concentrations are decreasing. Okay, so we can see that the rate for C is not equal to the rate for A, right? In order to make them equal, we need to do what? Well, first we need a negative sign in there. And then we can think about what could we multiply the rate of change of A by to get the rate of change of C. We know this is 0.5 for the setup we just showed. It's negative 0.5. How can I make that equal to positive 0.75? I have to multiply it by a number, in addition to the negative here, right? Because C is being produced, so its rate of change is positive, whereas A is being consumed, so its rate of change is negative. So I've got the negative in here. If this is 0.5 and this is 0.75, what do I have to multiply this by to make it equal? 4/3?
Yeah.
Nope.
I realized it was we're really bad at math.
What do I multiply 0.5 by to get 0.75?
0.25. Or 3 times.
I think so. 3 halves. Which also happens to be a ratio of their coefficients. Right? 3 and 2.
Is it really like it happens to be, or will it always?
No, it always will be. It always will be some ratio of their coefficients, right? Because we cannot produce C without consuming A, and so the rate at which C is produced is going to be directly related to the rate at which A is consumed, okay? But if they have different coefficients, they're not being produced and consumed at exactly the same rate, so we're going to need to multiply by those ratios of coefficients. All right? So if we want to then compare this to the rate of change of B over time, what am I going to have to do?
2 over 2, just 2.
Multiply by 2.
3.
B is 0.25, negative 0.25, right? And we want that to be equal to 0.75.
-3.
So I need a negative, and I need a 3. 3 over 1, which is the ratio of coefficients of C to B. Right? 3 to 1. Okay? So the reason I go through and explain all this is that sometimes we want to know the rate of a reaction. And we want to know the positive rate. How quickly is something being produced in a reaction? But sometimes it's not possible to actually measure that thing that's being produced directly. You might have to measure one of its reactants, and then using these sort of relationships, if we can find the rate at which a reactant is being consumed, like let's say we can measure this rate, then we can use this to calculate the rate of product being formed. Okay? All right. So this over here is basically just the definition of a rate. It's the change in concentration over change in time. And then we need to understand that for chemical reactions, there's going to be relationships for all the products and all the reactants in terms of those rates. Okay. Now, what we're also going to have to do, that is a pretty good chunk of 4A1. I'll talk a little bit more about 4A1 in a second, but I want to get into 4A2. 4A2 talks about what's called a rate law. A rate law. So we can measure the rates of reactions. For the case that I've drawn right here, the rate is constant. Right? If we look at any one of these reactants and products, the slope is constant. Well, it's not really because I drew it crap. Okay, but it should be constant, right? That's what I was going for. A constant rate over time. So it doesn't matter whether I have 10 molar of A, whether I have 5 molar of A, whether I have 1 molar of A or 0.0001 molar of A, it's still decreasing at a rate of 0.5 molar per second. Okay? That doesn't always happen. A lot of times the rate of a reaction is going to change as the concentrations of these things change. So it's more likely that when you do a reaction, you get some behavior where it might change very quickly at first, and then it might start to level off. Okay? So that the rate, if we actually calculate the slope at any given point here, the rate here is going to be different than the rate there. If it's not a constant rate, that means the concentrations of the things that are involved in the reaction are affecting how quickly the reaction occurs. Which actually makes a lot of sense, right? If I want to speed up a reaction, what are some ways I can do it? I can heat it up, we'll talk about that.
Increase concentration.
Increase the concentration, put more stuff in there, right? Makes sense that if you stick more stuff in there, you're going to get more reactions occurring, you're going to get a faster rate, okay? If there's very little stuff in there, there's very little chance that particles are going to find each other and collide and cause a reaction, and so the rate is going to be less, okay? But if this is still the balanced equation for this reaction, we're still going to have that same relationship between the values of the rates, right? So whatever this rate is here, if I were to calculate it, we know it should be different should be different than the rate of change of, so this is B, in the same period of time. Well, we're going to do an experiment in a minute, and maybe we'll actually measure those. Okay. And then C, since it's changing much faster than the others, this thing is going to have a steeper slope. All right, so we might get some graphs that look like that. If the graph is not linear, if it's not straight, we need to write what's called a rate law. And the rate law is some k value, some constant, a proportionality. Some constant times the concentration of the reactants. In this case, we'd have concentration of A and concentration of B raised to some exponents. This is what we call a rate law. A generic rate law. And most of what we do in kinetics is to try to come up with these rate laws. We want to look at some reaction where we want to say, is there a law that I can write that tells me for any concentrations that I plug in, for any amounts of stuff that I mix together in my reaction, what rate will that reaction occur at? This is super important. If I'm in some industry and we're mixing chemicals together to make some product, I need to know how much chemicals to mix together to make enough product to satisfy my demand, right? If I need to make some amount of this thing every hour, right? This equation is going to help me figure out what concentrations of things I need to put in there to make it happen, all right? Also could prevent us from doing something where we make the rate too fast. Maybe heat is generated in that reaction, and if we make it happen too fast, we generate too much heat, we can't get rid of it, and it's dangerous, right? So we want to know exactly how we can control this reaction and make it occur at the rate that we want to. Okay? Now, the rate we already defined. This K we're going to define a lot more, but this is what we call the rate constant. A and B are the concentrations of those individual reactants. And X and Y are what we call the orders with respect to A and B. The order of the reaction. So when I said that one of the reasons that we need to study kinetics is so that we can control reactions, that is true, but another reason to study kinetics is that if we know something about these rate laws, it can actually give us information about what collisions are occurring to make this reaction happen. So Big Idea 4 at the very beginning says that rates of chemical reactions are determined by the details of the molecular collisions. Right? These molecules have to collide in order for this reaction to occur. But we don't know in what way that happens. Does one A collide with a B first? And then whatever thing that makes collides with another A and eventually turns into our product? Or do the two A's collide first, make something, and then a B comes in and collides, and then they make the product? Or do all three collide right at the same time and mix together and make that product? Okay, that's where we're trying to go. We're trying to figure out what are the steps by which a reaction occurs, but in order to know that, the evidence we need, it comes from the rate law. Okay, so we're going to learn how to come up with these rate laws first, and then we're going to see how that connects to the actual collisions of the particles. So when I say the order with respect to A and B, for right now, those are just going to be integers to us. But eventually, that's going to tell us something about how many of those particles are colliding in a certain step of the reaction. All right? So let's do a reaction. Right? Sick of hearing you talk. All right, I'm going to give you a little preview of what we're going to do in one of our labs. In one of our labs, we're going to come back and use our buddies? Spectrophotometers. Because how the heck do we actually measure a concentration?
Yes.
Well, we could put stuff in there, right? When we did the Penny Lab, we mixed in a certain amount of copper sulfate solid, we put it in our volumetric flask, we added water, we shook it up, we added to the line, and we knew what its concentration was, right? But if a chemical reaction is happening, these concentrations are changing. We need a way of monitoring how much of that stuff is in there. And the best way that I can think of to do that is using a spectrophotometer. So if we come up with a Beer's law plot for a given substance, then all we have to do is stick it in here and measure its absorbance. We can use Beer's law to calculate its concentration. Okay? So I'm going to do the experiment here with a little bit of blue food coloring and some bleach. I'm going to put my lab coat on so I don't bleach my clothes, ruin even more outfits. So I want to do a couple of different experiments. So what I'm going to start with here is I've got two 250 milliliter beakers. I'm going to put 2 drops of blue food coloring into one. I'm going to put 4 drops in the other. So I'm going to start with 2 solutions of food coloring that are different concentration. We can see they're different concentrations because
One's darker than the other.
one's darker than the other, right? So it's the same substance, and the absorbance is higher, probably have a higher concentration. All right, I'm going to stick this, wow. Stick this into the spectrometer. Because what I need to know is what is a good wavelength to measure this thing at. So I'll hit collect. Now I've got 2 spectrometers hooked up. I've only got something in one of them for right now. All right, so we're worried about the top green line here. And if we hit our little x equals up on top, we can see that the maximum is occurring about 630 nanometers. So that's probably where I want to measure this thing. Okay? But I don't want to measure the absorbance versus the wavelength. I already know what wavelength I'm interested in. What I want to know is how does that absorbance change over time? So if I know the absorbance versus time, I can use Beer's law to get concentration over time. All right, so what we're going to do is we're going to go to experiment. You're going to do the same thing when we do our kinetics lab. We're going to go to, oh wait, I'm sorry, I got to stop it first. Can't make any changes without stopping. I'm going to go to experiment, data collection. By default, it goes to full spectrum, so it measures every wavelength and what absorbance it has. But what we want to do is we want to measure it over time. So I chose time-based here. Usually the duration starts out really short for some reason, like 10 seconds. So I just cranked it to 1,000 seconds, because who cares? Data's free, right? Am I going to get charged by the data point? So let's do 1,000 seconds. We'll hit done. Okay, we'll store this graph just in case we need it. Okay, and so now it pops up with a different set of axes. Now we have absorbance on the y-axis and we have time on the x-axis. All right, but we have a problem here. This is actually just a problem for me because I've got 2 spectrometers. They're actually set up to measure at different wavelengths. All right, you might find that when you do the experiment, you plug everything in, you go to time-based, and it picks some random wavelength that you didn't want. But what you can do is you can click up here. Here's my 2 spectrometers. Okay, this one is measuring at 629.4. That's actually the one we're interested in. Okay, but if I click on it, this little thing pops up. How much time do I sample for? How many samples do I mix together in average? Okay, we don't really need to worry about that. We want to configure the collection. I want to tell it, hey, don't use 629, use 630 or use 641 or something like that. Here's where you can actually tell it what wavelength to measure. Okay? So now at 630.1, I can mess with this other spectrometer so that we can use it later. 630.1. Okay, can't get exactly 0.1, 0.3 is close enough. Okay. So now it's time to do the experiment. So I'm going to take about 20 milliliters of this food coloring mixture, and I'm at about 10 milliliters of bleach. Mix them together, give it a little stir. No, what do I have to do?
Get rid of the air bubbles.
One for the homies.
Yeah, that.
Yes, air bubbles, if there's any of those, you want to tap
See,
those out,
call.
things like that. You gotta pour one out for the homies. All right, so now we got it going. Let's hit collect. Let's see what the heck happens.
It's only Tuesday. What? Oh my goodness.
You just said it was a long week.
Yeah.
Is it not like this?
It's only Tuesday.
This is like
Everything's
dragging
so
for me,
slow.
so.
All right, so this is interesting. We can see this thing going down. There's a bit of jaggedness to this, right? That's interesting.
So concentration is decreased.
So we can see the concentration of the food coloring is decreasing since its absorbance is decreasing. But what we're interested in is it decreasing linearly.
Yeah, more or less.
Seems like X.
Nay.
So we might have to let it run longer, right? 10 seconds wouldn't have been enough. We wouldn't have known in 10 seconds whether this thing is linear or not. We let it run for a while. It's not linear. It's not. Right? It's changing at a different rate now than it did at the very beginning. Okay?
So,
I'm going to let this run for a little bit longer. We're going to do some calculations, but I want to set up another experiment.
Mr. Bull,
What's up?
so like as the reaction's happening, can you just place it in the spec?
Yep.
Like every,
Yeah, you can pop it in there whenever you want.
so you could theoretically have it running for like 10 or 15 minutes if you want like the whole reaction happen. Like suppose
You
not,
can let this thing run as long as you want.
Okay.
Eventually, with this food coloring, the absorbance is going to get pretty close to zero, and it's going to be boring after a while. It's just going to be flat. But yeah, I mean, the thing is, if you're actually trying to do this experiment, you can't really mix the stuff together in the cuvette, right? You have to mix it together in some beaker, stir it up real good, and then pour it in. So there's always going to be a little bit of a lag time. But what you're going to see is most of what we're trying to do in this unit is to just see how the graph changes. Okay, so we don't really care where we start, we just care how the rate is changing as the concentrations change. And in this case, it definitely is. We start with a really high rate here when we had the most food coloring in the solution. Now we've got a really low rate down here when there's a lot less food coloring in there. All right, but we could freeze this. I'm gonna raise this up. We could actually calculate the rates. So I could calculate the rate at the beginning, and I could calculate the rate maybe at 50 seconds and try to compare them and see what happened. Okay? Now there's an issue. Ideally, what we'd like to do is to know what's called the instantaneous rate.
Oh.
Derivative.
It's a
The
math word.
derivative.
Yes, the derivative. I want to know what is the slope of the tangent line at exactly that point in time. Can I actually measure the instantaneous rate?
Yeah.
No, not with this. Unless I were to like fit this curve somehow and exactly know what the equation of this curve is, then maybe I could take the derivative at a certain point and it would tell me the slope, but we're not going to be able to do that. Okay? So what we can do though is just pick some points that are reasonably close together, find the slope there, and see where we're at. I'm going to stop the video. So yeah, ideally we want to pick a small enough time scale that we're not really, you know, spreading ourselves real far out. So we want to get as close to an instantaneous rate as we can, but we also have to be a little bit careful about those wiggles and things like that. Okay, so if we use the examine button here, I can go to the very beginning. At the very beginning, we were at an absorbance of 0.538 at time 0. If I go over to this point that I chose, the absorbance is down to 0.471. So 0.417 minus, what did I say the other time? 0.5.
5,
No,
1,
wait,
7, 5, 2, 5, 2, 6. That's my guess.
0.538.
Oh.
So we're doing actually this is the change in absorbance over change in time, but again, absorbance and concentration are directly related by Beer's law. So if I knew that Beer's law relationship, I could just change absorbances to concentration. That's what you will do in your lab. For right now, we're just going to use absorbances. Okay. Now the time difference, this is at time 8 seconds. This one was at 0 seconds. So 8 seconds minus 0 seconds. So what is the rate of change here?
Negative 0.121 over
8?
which is something I don't want to do like
I thought you had a calculator out.
Huh.
that.
She was doing mental math, that's good, aren't you proud of her?
You're right. You're right. I should be proud that you're doing this. 0.417 minus 0.538 over 8. 0.015, negative 0.015. And this is actually absorbance units per second. Normally we'd be in molar per second, okay? But I'm just trying to make a point here. If I move to the next area that I was talking about here, this is at time 50 seconds. We have an absorbance of 0.117. So I'll use that as my initial. 0.117, 50 seconds. I'll move the same, what did I do, 8 seconds in between for the first one. So we'll go to 58 seconds here. And we have 0.095 for our absorbance. Good thing nobody else is backing you up. Aisha, I'm talking to you.
Negative 0.00275.
00275. I hope you did that right. Okay, so we can see for sure we're getting very different rates at these 2 points in the graph, right?
Yes.
So what that means is that for this experiment, if A is our food coloring, then this X is not a 0. We know the order with respect to food coloring is not 0 because if it was 0 here, then it wouldn't matter what concentration we had, the rate should always have the same value. Okay, but as the concentration changes, since this is not a 0, that change in concentration is affecting the rate. Okay, we can actually figure out from this data what order the food coloring is. Okay, because what we did here is we calculated a rate, negative 0.015 absorbance units per second. So I could say for the first point in our experiment, that the rate was negative 0.015 absorbance units per second. We don't know what K was, but we knew that at that value, we were starting with an absorbance. I'm going to use absorbance in places of concentrations here, just to show you the point here. We were starting at that rate, that corresponded to our initial absorbance of 0.538. Now B is our bleach. We don't know much about our bleach right now, but that's okay. If we look at the second point, we can set up, it's the same generic rate law. So we can say the rate 2 is going to look very similar, but the values are all different. Now we have negative 0.00275 absorbance units per second. Well, that's because the concentration was less, right? For this point, we were starting with a concentration, or absorbance in this case, of 0.117. Now, how do we use these two equations to help us figure out the order with respect to x? Same thing that made you groan before.
So the
Maths. Maths. Actually, there's an easier way than doing a system of equations.
Oh, good.
What we can do is basically just set up a ratio. A ratio of the rate of experiment, the rate at time 1 to the rate at time 2 should be proportional to the other side's the equation, right?
since K is the same, can you cross it out?
Yes. That's actually why dividing this works really well. We don't know what this K value is. We haven't calculated it yet, but it's going to be the same. K has to be a constant for a given chemical reaction. It's not going to change just because I change the concentrations, right? Now, also, since I added the same amount of, well, I guess, was the concentration of bleach constant? Uh-oh.
Did you add 10 milliliters to each one?
I added 10 milliliters to each one. How much food coloring did I add?
Drops.
2 drops to that whole big beaker, and I only added a very small amount of that beaker. So this brings up a very interesting point. In 4A2 Part B, it says, in cases in which the concentration of any other reactant remain essentially constant during the course of the reaction, the order of a reaction with respect to a reactant concentration can be inferred from plots of the concentration of reactant versus time. Okay? So what I'm sort of doing here is, yes, we saw that it was a nonlinear relationship. Okay? That doesn't necessarily mean that it's zero order with respect to the food coloring. Because if the bleach's concentration was changing, which we know it has to be because it's being consumed as it reacts with the food coloring, maybe it's the bleach that's causing these rates to change. Okay? But because of the way I set up that experiment, I know that's not the case. Because the amount of bleach that I put in there was so much greater than the amount of food coloring. However much the food coloring is changing, it's only going to affect the change of the bleach by a very, very tiny amount. Okay? So if the bleach was 2 molar, the amount of food coloring I put in there, at most, is probably going to bring that bleach down to 1.95 molar. Okay? So that's one way that even though these aren't necessarily exactly constant, because I put so much in there, I can cross these off and assume they're constant. And so then we get a really simplified equation. The ratio of the rates should be equal to the ratios of the concentrations raised to some exponent. All right? But we got to do some math here. Because we have this concentration of A to the x over concentration of A to the x. Logs.
No.
Yeah. Yes! Why do you think they taught you logs? Because they wanted to torture you? Yeah, change the base of this log. It'll be... Oh, well. All right. Now, will you guys actually have to use logarithms? Yes, in the lab. On a quiz or a test? No.
Yeah.
On a quiz or a test, you can basically just do trial and error and plug in integers until you figure out what x makes these roughly equal to each other. But we're going to solve this by the rules of logarithms, because the rules of logarithms say a to the x over b to the x is the same as a over b to the x. That's actually not the rules of logarithms, that's just rules of exponents. Okay? So we could say to ourselves, well, if I'm plugging in the values, I had 0.538 up on top, we had 0.117 on the bottom, okay, but I really want to get that x out of there. So I'm going to say 0.538 over 0.117, that ratio to the x is the same as each of those to the x divided by each other, right? Okay, and then on the left side, we knew the initial rate was negative 0.015. The second one was 0.00275. Okay, so one person, well, we got two people out with our calculators. What do I get when I divide these two numbers? $5.45? Okay. What about when I divide these two numbers? $4.59. Okay. So, is there an integer that we can solve for x? No, it's not going to be a perfect integer value, but what integer do you think it's going to be close to?
It's 1.
Probably 1, right? Because if it was 0, this to the 0 would be 1, that's not equal to 5. This was a 2, 4 squared is 16, that's not even close to 5, this has got to be a 1 if we're making these integers, right? If I actually want to solve for it, I got to take the logarithm of both sides. So I'll take the log of 5.45, that's equal to the log of 4.59 to the x. Now the rules of logarithms are log of a to the x is equal to you guys didn't learn this rule?
1 over.
Just the base.
Oh, it's like a times
Doesn't matter.
log.
Now, if you have a number raised to an exponent, you can pop that exponent out of the logarithm. So this is equal to x times the logarithm. So I can actually say this is really x times the log of 4.59 equals the log of 5.45. So now I can say the log of 5.45 over the log of 4.59 should tell me the order with respect to the food coloring.
1.11.
Sorry?
1.11.
1.11. Pretty
Wait.
darn close.
So, since this is the order, aren't the only two possible answers 0 and 1?
No, 0, 1, and 2 actually.
Why?
What the order is telling us is how many of that molecule are involved in the slowest step of the reaction. So the least number of molecules you could need in this step would be 0, right? Food coloring could theoretically not be involved in the slowest collision of the reaction. Okay? In this case, since the x is 1, that tells us one food coloring molecule is colliding in the slowest step of this reaction. Okay? If it was 2, that means the slowest step of the reaction actually needs 2 food coloring molecules to collide with each other before something else can occur. So yeah, 0, 1, and 2 are really the only orders you can have. 3 is almost impossible. 3 molecules simultaneously colliding in exactly the right orientation, exactly the right place with exactly the right energy, it ain't gonna happen. Right? It'd be like if I blindfolded all of you, made you walk all around to the room like this randomly. What are the chances that 3 people are going to kiss right at the same time? I don't want to find out either. These are weird analogies. Okay. So this actually is what we call the method of initial rates, or very similar to what we use the method of initial rates. what I did was I looked at the rate at two different times, really for two different concentrations of food coloring, and by comparing the ratios of their rate laws, I was able to figure out the order with one reactant. Okay, we're going to do a lab based on that. It's not going to be a graphical thing. What we're going to do is we're going to measure a reaction that we can actually time. So we'll see how much time this reaction occurs, and in that amount of time we can calculate how much stuff has reacted, so we'll be able to get our rate. What we're going to do is we're going to play around with the concentrations of these things and see what happens. So we might double the concentration of something and see what happens to its rate as we double it. Right? If the rate stays constant, that thing has zero order. But if I double the concentration of something and the rate doubles, then it's first order. If I double the concentration and the rate quadruples, it must be second order. Right? My generic rate law went. Right? But if I double this and the rate doubles, assuming this is constant, then the order is 1. If I double this and this quadruples, then the rate should be, or the order should be 2. Okay? All right. We'll do a couple of practice problems in a minute with that, I think. Okay? I told you I was going to do a lot of math today. Yeah? Oh, I told the other class. All right. Now we're going to do a little calculus. Yikes. Calculus. What I just wrote for you is a rate law. But remember, we determined the rate based on that tangent line, right? The instantaneous rate. So really, we're looking at the derivatives, right? We're looking at the slope of this line and how it changes as the concentrations change. So this equation is actually what we call the differential rate law, right? It's like a slope sort of rate law. What we can do is we can change these rate laws. Instead of being how the rate changes as the concentration changes, I can come up with a different form of these rate laws that show how the concentrations change over time, which is actually a lot closer to what this graph was originally set up, right? This graph was originally set up as a concentration versus time graph. So what I'm going to do is I'm going to do a little bit of calculus to these rate laws and see what will the graph actually look like. Remember I said before that if it was zero order, then the concentration should just change consistently over time, right? But with the food coloring experiment, we saw that the concentration was not constant over time. We got some sort of changing slope, right? But what we're going to try to do is we're going to say, well, okay, if concentration versus time is linear, that's going to tell us something about the order. But if it's not linear, what do we do? Okay, so let me do some calculus here. It's actually going to depend on the order. So I'm going to do it for a zero order reaction. I'm going to do it for a first order and for a second order. So for a first order reaction, for a zero order, the rate law is going to look like this. Again, I'm only going to worry about one reactant right now. So it's that part from 4A2 where it says, let's set up our reaction so that the other thing isn't changing very much. That's what I did with the bleach, right? So all I'm really worried about is what is the rate law with respect to A. Okay, now if it's A to the 0, that's really 1, right? So this rate should be constant, just like we saw in the first graph. What's rate though? How do we define the rate?
Concentration versus time.
The change in concentration versus change in time. So this rate is really the change in the concentration of A over the change in time. And that value is constant, right? Now, I don't think, anybody at BC Cap? Have you done this yet? Yeah?
Yeah.
Ah. Who's never seen that symbol before?
Well, everyone else.
Everyone else? You've seen it before. It's not an S.
Integral.
That's the integral sign. What I want to do is I want to take the integral of this. Right? Now, who's learned about derivatives? Almost everybody, right? What's a derivative?
The slope of a slope.
It's the slope of the graph at a particular point, right? It's the slope of the tangent line at that graph, right? It's really showing us how that graph is changing over time, okay? But I want to go the other way. An integral is going the other way. So if you learn how to take a function and find its derivative,
Take the derivative.
to take an integral, you're just going backwards. So you're asking the question, what function would, if I took its derivative, give me this? In fact, the integral is sometimes called the antiderivative. Right? You're going backwards from what you would do in a derivative. Now I can't really do that yet because I have two variables on the same side. So first thing I have to do is I'm going to move this delta t to the other side. So I'm going to say the change in concentration of A is equal to K change in T. Now I can take the integral of both sides. What do I get? Well, the integral of the change in something would just be that thing, right? Like the integral, well, I guess like if I had x and I took the derivative, what's the derivative of x? 1 dx.
One dx.
Right?
One dx.
Yeah. So I already have the sort of dx here, so I'm asking what did that come from if I took the derivative? Well, it came from x, right? So this is really concentration. Right? If I take the derivative of concentration, I get change in concentration, dx. I'm using the delta notation, okay? Now, when you take integrals, you also have to have a starting and an ending, right? So I'm going to go from like 0 to t here. Okay? So this is really then the concentration at some time minus the concentration at time 0 on the left side, right? So those are sort of the limits of integration. On the right side, I have just some constant times dt essentially, right? So let's say it was 3 dt. What function would I take the derivative of and get 3 dt? 3t, right? If I took the derivative of 3t, it would be 3 dt, right? So if I have just k dt and I'm taking the integral of it, that must have come from something like kt. Why did I just leave it alone? It's just a number, it's just a constant. It's not a variable. Okay? Now we have the sort of same situation here where we're going between two limits, but for t, the other limit is just 0. So we don't have to subtract 0 from this, that's pointless, right? Okay? So what we actually get here is a function, and this is what we call the integrated rate law. The 0th order, or 0th order, integrated rate law. I've integrated the 0th order differential rate law, and I've got the same function basically in a different form. Okay, so depending on what I'm trying to do, I might use very different forms of this rate law. If I want to know how the rate is affected by concentrations, I might use this one. But if I want to know what the concentration is going to be at a certain time, then I want to use this one. Okay? This one is nice because if I know the initial concentration of the thing I'm putting in there, and if I know my K value, which we'll be able to calculate, I actually should have done that for our experiment. Once we knew the order here, we could have plugged in the concentration, the rate, and 1 now, and we could have solved for x, I guess, in any one of these equations. And we could have actually calculated numerically what K is. All right, it's going to be the same K here. All right, but if I know my initial concentration and I know my K value, I can plug in some time and predict what the new concentration is going to be. All right? The other thing about this integrated rate law is it tells me that if I graph the concentration versus time, it should be a straight line. Right? Because I have concentrations on this side, I have T on this side, so it's basically like a Y equals mx, and really if I move this to the other side, that could be my plus B. Right? So sometimes you'll see it that way. Actually, take out your equation sheets. Ooh, no. They don't give it to you. Kinetics is the very bottom of the first page. They do not give you the zero order integrated rate law. I guess because it's so simple. Especially if I move this over to the other side, I would get that the concentration at some given time is equal to KT plus our initial concentration.
So is this like when it's 1 over the concentration of A, T? Is that like different than?
Okay, so there are two equations on here under kinetics. Those are two of the solutions of what I'm about to do here. Okay? So what I mentioned was that if the graph isn't straight, if the graph is straight, we know it's zero ordered because it's fitting this type of a function. It's saying that the concentration is changing linearly with respect to time. Whatever this K value is, that determines the slope, right? So for zero order, the graph is going to be concentration versus time. It's going to be linear, and the slope is going to equal K. But now I got to do it for first order. For first order, we're going to have rate equals K times A to the 1. That's our differential rate law. But again, rate is really the change in concentration over the change in time. And now I want to integrate both sides. I still have to separate my variables. So I have to move all my concentrations to one side, all my times to the other side. So what I end up with when I multiply both sides by delta T and divide both sides by the concentration of A is change in concentration of A over the concentration of A is equal to K dt.
Wait, so the integral sign in the first line where you have it doesn't do anything, right?
Well, I'm just rearranging it first. I haven't actually taken the integral yet. I'm just moving the T over to this side and the concentration of A over to that side. That's all I do. Now I'm going to take the integral. Okay? But basically, again, the integral is asking what function could I take the derivative of and give me dA over A? What function's derivative gives you 1 over x dx? Natural log. Right? The natural log, the ln. Okay? So this function must have come from a natural log. All right, we got that same sort of 0 to t situation going on here. So we could say the natural log at time t minus the natural log of the concentration of A at time 0. That's really the solution to the left side. The right side is kt. Well, it's k delta t. I'm integrating it. So I'm going to get the same answer on the right side. I'm going to get kt. Okay? And so this is the first order integrated rate law. This is what the first order function looks like if we integrate it. And that is your first equation under kinetics.
Why is the KT negative on the equation sheet?
Why is the KT negative? Fantastic question. Why? I think the answer answer is because we always want our rate to be a positive number, right? But if A is a reactant, it's decreasing. So when we talk about this change, whatever the natural log is at some final time minus the natural log at the initial time, it's going to end up being a negative value, right? And so if we want our K to be a positive number, we want to put a negative. It's sort of the same situation as when I was saying it depends on how we define our rate law, if we're talking in terms of production of a product or the removal of a reactant. Okay, so I'm pretty sure it's because we're talking about these are reactants, but this rate here is supposed to be a positive value based on some production of a product or something like that. Yeah. That's what I'm saying. Okay, so what this tells us actually is that if our reaction is actually first order, if we graph the natural log of this stuff versus time, that should give us a straight line. Because if I do a little rearranging here, natural log of A at some time is equal to minus KT plus the natural log of the initial concentration. And this looks like a y equals mx plus b if I make my y natural log of the concentration and I make my x time. So, what I can do is I can actually take our data from this experiment and I can see whether this is in fact first order. Okay? If you graph natural log of x, you might see what shape natural log of x looks like. You might say, oh, it looks pretty similar. This is first order. But we don't know unless we actually calculate it. So what I'm going to do, if I can, to take this data, I'm going to use one of my best friends there, Excel. These are times. It's time in seconds. These are my absorbance, which is unitless. Now again, these should be concentrations, but I don't have time to figure out the Beer's law function and convert my absorbances to concentrations. You guys will do that in the lab. I'm going to take the natural log, though, of the absorbance. How do I do that? I hit equals ln, open parentheses. Then I click on the cell next to it that I want to take the natural log of. Close my parentheses, hit enter. Boom. So there's my natural log. And I can move the cursor to this bottom right corner of this box. It turns into a little plus. And I'll just do that. I'll just take the natural log of all these bad boys. Oh, man. I don't know why it ignored some of this. Didn't take data points here, so I want to get rid of those because if I try to plot num versus time, it's going to be very confusing. That should be enough. Okay, so if I plot natural log versus time, let's see how it looks. Boom. Pretty darn linear, right? So the linearity of that function is telling us that this reaction is first order with respect to food color. Okay? If it wasn't first order, this wouldn't be a straight line. Well, I should say it looks like a straight line. The only way to know for sure is to add a trend line, display the equation, and display the r squared. And to make sure that you're using a linear function. Okay? So it gives us a relationship, y equals negative 0.034x minus 0.6399. R squared is 0.9975. That's pretty good. Pretty good. It's probably first order. But let's just double check. What do we need to do to test to see whether it's second order? I gotta take the integral of the second order rate equation, which is going to be rate rate equals k times a to the 2. This is really change in the concentration of A over change in time is equal to k times a to the 2. So this is dA over a squared equals k dt. Now I'll take the integral of both sides. Oh boy.
1 over x squared. So
So we want to know what function, when we take the derivative, will give us 1 over x squared.
1 x squared. We go with
Remember how derivatives work, right? If I'm taking the derivative of x squared, what is that, ddx? No, I mean, how do I show the derivative?
Oh, dy dx.
Okay, so this is going to equal 2x, right? Because what do? We take this,
the front.
move it out in front, make the number down, go down even more. So now we're really getting, our answer here is we're getting x to the minus 2. So we're asking ourselves, what function would have given us the derivative x to the minus 2?
Oh,
Oh, I know my
1/3
x.
x.
It's got to be one higher of a exponent, right? Which is the reason we had to use the logarithms here.
That would be negative, but we-
Because if I had x was,
that's negative 1x. So,
yeah, it's actually got to be negative here, right?
yeah.
So if I had negative x to the minus 1, I'd multiply the negative 1 out in front, that would cancel with this, drop this exponent down one more, it'd be x to the negative 2. That's where we go. All right? So this, we're actually getting 1 over a at some time minus 1 over a at time 0. But that whole thing is actually negative. And again, that equals kt.
Why'd you make that side
Or does it equal
instead of
negative
KT?
kt? What?
Why'd you make that side negative instead of KT?
Over here?
No, for the second one.
Well, because we got the negative here, right? We had to have a negative here in order to not have a negative.
Oh, and so then do they want you to have a negative KT again, so that's why on the equation sheet, it's just both positive?
Yeah, so if this is really equal to negative kt, if we have that problem of this is a reactant, but this rate is talking about products here, then these negatives are actually going to cancel out. So that should give you the second equation on your equation sheet. 1 over a to the t minus 1 over a naught to the t is equal to kt. All right? So what that tells us is, if we want to, this board is nasty looking. Sorry. I put summaries of this on all the AP notes that I shared with you earlier today. All right? But basically, if I rearrange this to make it look like a y equals mx plus b, what I want to graph is 1 over the concentration. If 1 over the concentration versus time is constant, then it's actually second order. So I can try that. I can do that test here for this data. I'll make another column that's 1 over the concentration of absorbent, or sorry, we're using absorbance, but we'll do 1 over the absorbance. Whoops. 1 over that number. Drag these down. Oh. Divide by 0, that's the worst. That'll be like 0. Okay, now I'll graph 1 over of the absorbance versus time. How's it look? Not as linear, right? So let's add the trend line equation in the r squared, and let's see, yeah, 0.95, it's definitely not as linear as this test. And I think we could see from the raw data, it clearly wasn't linear with just concentration versus time, right? So it's got to be first order. All right? This is called the method of integrated rates. problem? Practice problems for this method are pretty easy. Basically, all you have to do is make 3 different graphs and see which graph is a straight line. If concentration versus time is a straight line, it's 0 order, and the slope is your k value. If natural log of concentration versus time is linear, that's first order, and your slope is negative k, right? See how our natural log one is negative? We got a negative number here, so here's our k value. Negative 0.0304 should be our k. All right, and then if it's second order, graphing 1 over the concentration versus time should give you a straight line. All right. So that's sort of a graphical method. Let's go back and let's do a problem like I kind of did at the beginning with the method of initial rates. Here's a problem from the book, problem 79. A study was made of the effect of the hydroxide concentration on the rate of the reaction I plus OCl minus forms IO and Cl minus. Okay, which is interesting because hydroxide is not even in this reaction, right? Okay, but it's still possible that hydroxide could have an effect. So what they've done here, they've carried out a whole bunch of different reactions using a whole bunch of different concentrations of these 3 ingredients. And then what they've done is somehow measured the initial rate. So almost like when we took that tangent line at the very beginning of the graph for food coloring, right? That's kind of what they're doing here. They're saying, what is that rate at the very beginning if I use these different concentrations of these reactants? So what we're going to do is we're going to try to compare 2 different experiments. And since we know that the rate law can be written as some constant times concentration of reactants raised to some exponents, and since they're saying that hydroxide might affect this as well, even though it's not a reactant, I'm going to put it in there and give it its own exponent. So this is what our generic rate law looks like. O is going to have rate, O is going to have some K, some constant. We're going to have our concentrations. They're going to be raised to exponents that we have to do experiments to determine. All right. Now, how do we use this? There's a whole lot of numbers up there. In this method, notice none of these concentrations is like way, way higher than the others, right? I mean, this is 10 times higher than this, so I guess it's 100 times higher than that. But none of these are so much higher than the other that we can assume that they're constant throughout the reaction. We don't need to, though, because when we look at just experiment 1 and 2, what did we really do? We kept the concentration of hydroxide the same. So if I'm comparing the rate of reaction 1 with its values to the rate of reaction 2 with its values, because of the way that I've set up my concentrations, when I'm comparing these two, I don't have to worry about hydroxide. It's the same concentration in both experiments. So whatever Z is, if this is 0.1 over Z, and I'm dividing it by 0.10 over Z, it's just going to be 1 for any exponent, right? The OCl minus in these 2 experiments has also been set up so that it is identical concentration, 0.012 to the Y, right? That's going to cancel out as well. Those are both 1. So really all we're worried about in this first 2 is how did we change the concentration of I minus? Well, it looks like we doubled it. Again, the K is going to be constant, so we don't have to worry about that. The K's are going to cancel out. But the rate definitely changed. 9.4 times 10 to the minus third. And then it changed to 18.7 times 10 to the minus third. Oh, that was a convenient number. Even though it's terrible scientific notation. Why'd they use that number? Yeah, it's like about twice as much here. So the rate doubled, and what did we do to the concentration?
It also doubled.
It also doubled. So X has to be first order, 1, right? If I actually plug this in, I'm going to get about 0.5 here. I'm going to get 0.5 here. The only number that can make those equal is 1. So we just figured out the order with respect to the iodide. This is really nice, because now we don't have to worry about keeping I minus constant. Even though they were nice to us, and look at all the setups where I minus is 0.0013. That's pretty nice. And I can pick just about any of the other ones and I minus will be constant. But I actually don't need to. Even if they'd given me all different concentrations of I minus here, it doesn't matter now. I know the order of I minus is 1, so even if these weren't the same, I'd still just raise them to 1 power and just make it part of my calculation. Okay? Hopefully we'll do an example where you'll see what the heck I'm talking about. Okay, so we got our I minus, now we got to try to go after the OCl minus. So we want to try to find some experiments where OCl minus is changing, but the others are not. Anybody see ones we could use? We could use the third and the fourth. In the third and the fourth, I minus is constant, OH is constant. All we're doing is changing the OCl minus. So let's do that. We'll say the rate for the third compared to the rate for the fourth is equal to K times I minus for the third raised to 1, OCl minus for the third raised to the Y, OH minus for the third raised to the Z. Now this looks really nasty. This is a lot of work. And I'm really writing down a lot more than you probably need to. If you're doing a free response type of problem, do you need to write all this? Probably not. You could just go ahead and plug everything into the rate law. Do you need to do the logarithms and stuff? No, you could probably say that, well, the only integer that's going to give us anything close to equality is x equals 1. Okay? So probably these 2 lines, or these 3 lines would be the most important, but I'm showing it for total completeness, everything that I'm trying to do here. So in experiment 3, it's 4.7 times 10 to the minus third molar per second. Experiment 4, it's 14 times 10 to the minus third. All right. Now the K's are going to cancel. I minus, even though it's constant here, well, I guess because it's constant here, I can cancel it out. I'm not even going to worry about it. It's a waste of time. OH minus is also constant, so I don't have to worry about that. So really, I just need to do the ratio of the OCl minus. So in experiment 3, it was 0.0060 molar. In experiment 4, it was 0.018 molar. And so basically, 0.006 over 0.018, 6 over 18 is a third, right? 0.33. So 0.333 to the y is equal to this. Well, let's see, 4.7 is pretty close to 5. This is close to 15. 5 over 15, that's got to be about 0.33 as well. So y is 1. So it's first order in iodide. It's also first order in OCl minus. Now we got to try to figure out the order with respect to hydroxide. What 2 experiments should I use?
Those 2.
Probably these 2 are the best, right? What is this, the 5th and the 6th? All right, and we could probably just do this by inspection at this point, right? This is constant, we don't have to worry about it. This is constant. What did we do to the hydroxide? We quadrupled it if you're going from this one to this one. We 1/4ed it if you're going this way, right? So we quadrupled this. What happened to the rate?
You roughly quadrupled it. A little more.
Actually, no, we
No
didn't.
one time.
What's 4 times 4, 16?
I thought this was going to be easy. We plug in the numbers. We have 0.050 over 0.20 for my concentrations. My rates, I have 18.7 times 10 to the minus third over 4.7 times 10 to the minus third. What's 18.7 over 4.7? 3.97?
So there's like 4.
No! What's this?
0.25.
Oh, 1/4.
1/4, 0.25. Right? This is kind of weird. We quadrupled the amount of stuff that was in there, but the rate, sorry, we quadrupled the concentration, but the rate went down. Is there a number that we could get for z? Well, we'd have to take the natural log of 4, divide it by the natural log of 0.25. What do we get? Solve for z here.
It's -1.
-1?
Yeah.
Can you have a negative order?
Yes. Z equals -1. You can have negative orders. What does that mean, though?
That it never collides.
Well,
If
let's just think about it in terms of the rate. What does it mean if this is -1 in terms of how it's going to affect the rate? In other words, now we know our rate law for this reaction is rate equals K times I minus to the 1, OCl minus to the 1, OH minus to the -1. So if I increase these concentrations, it's going to increase my rate, right? The higher these are, since their exponent is 1, the higher the rate is going to be. What happens if I put more hydroxide in here?
it'll decrease.
It'll decrease the rate. So negative exponents are possible, but only for things we call inhibitors. OH minus is actually inhibiting this reaction. The more OH minus is in there, the slower the reaction occurs. Maybe OH minus is undergoing some other reaction, which is preventing the reaction we're trying to do. Okay, I don't know what, but for some reason, OH minus is slowing us down, so we call that an inhibitor. So if you ever calculate a negative exponent, that's why. It's not that you did something wrong, well, you might have. But it's possible that that thing is an inhibitor. All right? Tomorrow I'll show you why it's stuck in here.
Yeah. Someone